a polynomial, right? The numerator is a polynomial. And it just so happens that we're throwing in another polynomial in the denominator. So chapter 4 builds on chapter 3 really nicely because now we're saying make a fraction out of two polynomials. And then what does that look like? You know, if you take a polynomial and divide it by another polynomial, what does the graph look like? What kind of properties does the graph have? And that's what we're doing in both of these. Okay, so you build a polynomial, what can the graph look like? Where are the x-intercepts? Where's the y-intercept? If you build a fraction out of two polynomials, what does the graph look like? Where are the x-intercepts? Where's the y-intercept? What does it look like? So that's what we're doing in chapter 3 and 4. Sounds exciting, right? I know it's 8 a.m. on a Wednesday. Is today Wednesday? Today's Wednesday. Yeah, very exciting. So today we'll start with chapter 3, and I'd like to preview the whole section by giving some main ideas, and then we'll do the class notes. So first, everybody, let's look at this page. You took 3 gifts back there. This is the first one I'd like us to look at. It starts at the top, says college algebra, recall solving a quadratic equation using factoring. So everyone take that one out. So, does everyone have that? There you go. All right. So recall this basic technique, because this basic technique is what we will build on to study polynomials in general, which is really interesting, that being able to solve a quadratic, x to the power of 2, can give you enough insight to solve something like x to the power of 7. This is really interesting. So how would we solve this? So everybody start off by writing it down in your own handwriting, x squared plus 2x minus 15 equals 0. And keep in mind, we're asking the most fundamental, basic question. What number can I plug into x to make this true? That's always what we're asking. What number can I plug in for x to make this true? So anybody want to take a guess? What number can I plug in for x to make this true?
5.
Maybe 5 and 3?
3 and negative 3.
Maybe negative 3 and 5? Let's try 5 first, see if that works. If I plug in 5, I would get 5 squared, which is 25, plus 2 times 5, which is 10, and then minus 15. And oh, that didn't work so much. 35 minus 15 is 20 equals 0. So 5 is not a solution. So what was the other option? Wait, did I do that wrong?
Yeah, well, you did it right, but it's supposed to be negative 5.
Right, it should be negative 5. So let's try negative 5. If I plug in negative 5 squared is 25. 2 times negative 5 is minus 10, minus 15. Now, is that true? 25 minus 10 is 15, 15 minus 15 is 0. So yes. So because this was a true statement, now I can say for sure that x equals negative 5 is a solution. So how many solutions will this equation have?
2.
At most 2, right? At most 2. So far I found 1. Is there another solution? Let's try 3. So if I plug 3 in, so 3 squared is 9, plus 2 times 3 is 6, minus 15. Is that true? 9 6 is 15, 15 minus 15. Yes, that was true. So now I know that x equals 3 is a solution. So right now, just by kind of guessing around, I mean, it wasn't pure guessing. I think you all did the factoring and saw that 5 times 3 was 15 and adds a 2. But now we know negative 5 and 3, we're done. Because we know from theory that we have at most 2 solutions. We found 2 solutions, so we're done. However, we don't want to do this guesswork or doing anything in our head. The proper procedure, now do this with me, is you go ahead and factor it. You say, what multiplies to make negative 15 that adds to make 2? So you make a factor table, and you say, well, 15 is either 1 and 15 or 3 and 5. I want to multiply to make a negative 15, which means I'm multiplying a positive times a negative. So one number is positive, one is negative. I have to add them to get a positive 2. So that would be a positive 5 and a negative 3. So there's our analysis. Now we get to just write down the answer. So it's x minus 3, x plus 5. So that's the first thing. We just factored. Everybody's third favorite F word in mathematics, factoring. So now that we have this times this equals 0, what can we use? Yeah, the zero product rule. The zero product rule says that if this times this is 0, one of those has to be 0. So now we draw little arrows and we say, well, either x minus 3 is 0 or x plus 5 is 0. And maybe you've already got a gut instinct here that whatever you see inside the parenthesis, you just change the sign of that number and that's your answer. And that's a good intuition, but it's still a good practice to go ahead and solve it. So yeah, it is x equals 3. And then this one, you subtract 5 on both sides. It is x equals negative 5. Why is it that in general you can just change the sign of that number and say that that's your answer? Yeah, and that has the result of you adding by the opposite sign to move it over to the other side, and that's why the sign changes. Okay, so there's our 3 and negative 5 that we just came up with, and this is when we say we're done. This was our whole principle for solving a quadratic. You take your quadratic, which is an addition problem, something plus something plus something, you convert it into a multiplication problem. So this was an addition problem, this was a multiplication problem. You convert it into a multiplication problem so that you can use the zero product rule. And that allows you to set each of those factors. So we call this a factor, we call it a factor. You set each factor equal to 0, and then you can finish the problem. Notice what we did was we took a hard problem, x squared, and we reduced it to 2 simple problems with just x. That's kind of the key to this method, is you take a hard problem and you reduce it to 2 simpler problems. Okay, so that's the idea. What we want to do over the course of the next few weeks is take even something like this, x to the 5th, and since that's x to the power of 5, that means you have x times itself 5 times. We will ultimately be able to take this problem, which is an addition problem. You all agree this is an addition problem? Because it's something plus something plus something plus something. We're going to be able to take this and rewrite it as a factor times a factor times a factor times a factor times a factor. Let's say that was 0. Because now I have x plus or minus something, 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 x plus or minus. So in the end, what we would have is something that looks like this. Is we will take this addition problem, break it down into this multiplication problem, like a massive factoring job, right? You're no longer just factoring what multiplies to make the last number that adds to make the middle number. We have a massive factoring job ahead of us to rewrite this addition problem as a multiplication problem. But once you do, what could you do with all these factors? Zero product rule. And so at this point, you'd say, well, if that times that times that times that times that equals 0, then one of those had better be equal to 0, and in fact, all of them would be equal to 0. And you would sit there and say, all of them equal to 0, and of course, you could just change the sign of every number, and you'd say, hey, the x-intercepts are -5, +4, -8, +1, and -3. And then you'd be done solving for your x-intercepts. So once you have it, a polynomial, as a multiplication problem, factor, you're done finding the x-intercepts. The real question is, how do we go from here to here? That's like the $1,000,000 question. How do you take a polynomial as an addition problem and rewrite it as a multiplication problem? That right there is very, very challenging and took hundreds of years of mathematical development in the 1500s and the 1600s for people to figure out how to do that. I can tell everyone's really excited by this theory. Like, oh my goodness, this theory is exciting. Tell me more, Mr. G. Wow, this is great. Okay, so looking at these two problems then, once you have a polynomial, again, we're looking at quadratics, but we're pretending that we're going to build up to some bigger polynomial. How would we make those graphs?
Solve for the x-intercepts, and then you could potentially just use the vertex formula.
Sure, you could potentially use the vertex formula. Yeah, so what we want to do is we're going to factor both of those, get the x-intercepts, and then based on our general knowledge of what a quadratic or a parabola would look like, once you have the x-intercepts, we can basically just make a little sketch. Okay, so let's all do that together. This first one, x squared plus 4x plus 3, you can go ahead and factor that. What multiplies to make 3 that adds to make 4? So it's going to be x plus 3, x plus 1. So all this is always pretending to be equal to 0. And then we solve both of those. So now we know that my x-intercepts are -3 and -1. So now, folks, go to your graph. Go onto your graph, find -1 and -3 with little dots. And then essentially what I'm saying is you can just make a swoop. You can say, well, those are my x-intercepts, so I know my graph is going to look something like this. It's just a rough sketch, but it's just enough to let you and your audience know what you're expecting the answer to look like. If we wanted to be even more specific, what could we also add? Yeah, we could add the y-intercept, because remember, the last number is the y-intercept. So now you can go ahead and put on 1, 2, 3, put the y-intercept on there as well, and now you've got a really nice sketch, because you know where your parabola is. So go to the next one as well. Go ahead and take your x squared minus 8x plus 12. Factor it, plot the x-intercepts, and the y-intercept. Well, you won't be able to fit the y-intercept on there because the y-intercept is 12 and the graph only goes up to 8. But definitely factor it, find those x-intercepts, and then make a quick sketch of your graph. Oh, nice. Yeah. So did everybody get x minus 2, x minus 6? Which then you change the signs or set them all equal to 0, and then you get x equals 2 and 6. So on your graph, you go over to the right at 2, and then 3, 4, 5, 6. And then you can basically just make a little sketch. So these are the principles that we want to apply to longer polynomials that start with something other than x squared. So if we all, what, do we turn the page? Yeah, turn the page. So I've got an open-ended question there for you. What can you say about any function written in the form f of x equals x minus a, x minus b, x minus c, dot, 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 x minus z? What can you say about a function that you write in that form? And if you want to, you could jot a specific example. You could say, let's say f of x is equal to x minus, we'll say 7, x minus 3, x minus negative 1, and x minus negative 5. What can we say about that function that we already know for sure?
Those would be x-intercepts.
Yeah, now we know where all the x-intercepts are, because by the zero product rule, this times this times this times this, if I set that equal to 0, and then I set each of these equal to 0, notice these ones, you just change the sign, so that's, I have an x-intercept at 7 and 3. What about this? I did x minus negative 1. Yeah, I mean, really that's plus 1, and then if you change the sign, that's minus 1. So that x-intercept would be negative 1. And then this is really x plus 5, so if you change the sign, it's really minus 5. I wrote it like this because generally speaking, we write down the terms as x minus something, x minus something, x minus something, x minus something. You didn't have to, though. I could have just left it as x plus 1. And then again, you would know to change that sign, and then those are your x-intercepts. So now what do? We have this function written in factored form, and we know that each factor represents an x-intercept. That's what I would like to write down. Each factor represents an x-intercept. And so if I now made a graph, I would say, well, I know that I have an x-intercept at 1, 2, 3, 4, 5, 6, 7 over here, an x-intercept at 3, an x-intercept at negative 1, and an x-intercept at 2, 3, 4, 5. I've got these x-intercepts now. How do I sketch the rest of the graph? What exactly do I do now to finish it off?
You could factor the problem to understand how the graph shape is going to be, but also give you y-intercept.
By factor, you mean FOIL?
Formula.
Right. So now here's the thought. We could take all 4 of these now and FOIL them all together. Now I want you to appreciate that foiling that many terms together is a big, laborious task. I mean, it's one thing just to FOIL together x minus 7 times x minus 3. I can just write that down. That'd be x squared minus 10x plus 21. But now let's say I want to multiply that times x plus 1. And then after that, I still have to multiply it times x plus 5. So just appreciate, you don't have to write this down. But if I did want to multiply now this term times that term, I'd have to distribute the x to all 3 terms. So that'd be x cubed minus 10x squared plus 21x. Okay, so that's that. And then I'd have to distribute the 1 to all 3 terms. So then I'd have, furthermore, plus 1x squared minus 10x plus 21. And then I'd have to combine all those like terms and get x cubed minus 9x squared plus 11x plus 21. And now I'm not even done because I still have to multiply that times x plus 5. So then what would I have to do? I'd have to distribute the x to all 4 of those terms, and then distribute the 5 to all 4 of those terms. And then I'd have to write all of those down, combine all my like terms, and then I'd be done. And I'd have some massive thing that starts with x to the 4th, plus a whole bunch of terms, plus 105. Why was I able to confidently write down x to the 4th?
Because there's 4 roots or you know that the exponent.
Yeah, that's certainly one way to look at it, is you know that you have 4 factors. Each of them has an x. So when you finish folding it all together, you're going to have an x to the 4th as your leading term. And that's true. And then why was I able to confidently write down 105?
It's 21 plus 4 times 5 gives you 5 for your
Yeah.
5%.
For sure. And so where could I have gotten 105 from, though, even before that?
By multiplying all the numbers together.
Yeah, just multiplying all those numbers together. You'll notice that the leading term, x to the 4th, is the first term, x times x times x times x, that's x to the 4th. And then the final term, 105, is all the numbers multiplied together, -7 times -3 times 1 times 5. So even without doing all this intermediary FOIL, I could just look at that and immediately say, hey, my polynomial is x to the 4th plus 105. The middle terms, I'm a little fuzzy. I'd have to do a lot of work and a lot of time to get all those terms. But I can immediately say what the first term is and what the last term is. So now here's the benefit. The last term is my y-intercept. Because each of these terms has an x in it. So now I'm down to f of x equals x to the 4th plus something x cubed plus something x squared. And if I plug 0 in, what happens to all the terms with an x in it? Yeah, all those x terms go away, and I'm just left with 105. So I know that my y-intercept now is 105. And this, the leading term, x to the 4th, represents my end behavior. Have you folks ever heard the phrase end behavior? Okay, so let's talk about it. So thus, writing a function in factored form is a way of listing and creating x-intercepts. So first of all, if you can write it like that, now you know all the x-intercepts. And then finally, the end behavior is given to you by the first term. Okay, the last term was the y-intercept. The first term is going to give you end behavior. So let's take a look on Desmos and see some end behavior. So, Desmos. If you have x to the power of 2, we all know it's a parabola. What if I have any even exponent? So x to the power of 4. What does that look like? Yeah, still a parabola. X to the power of 6, x to the power of 8, x to the power of 10, x to the power of 12, x to the power of 14, x to the power of 16. It still looks like a parabola. What do you notice is happening? Yeah, it changes a little bit. And in fact, what's happening is that the parabola is getting flatter along the bottom. I don't know if you noticed that happen. Let's watch that again. If you start with squared, notice how nice and curvy it is. And it really only lands or touches down at the 0. But as it increases the power of 4, the parabola is kind of like getting heavier and squishing down and kind of riding down along the x-axis longer and more. Okay, so does everyone see that? And I can make it more exaggerated by making my exponent really big, like 30. So it's still an even power. So what will any even powered parabola look like? It'll still look like a parabola. It'll be a little flatter along the bottom, but it'll still essentially be a parabola. So you can all go ahead and make a note now at the bottom of that page there, talking about end behavior. So any x to the power of an even number will look like essentially a parabola. But what I really want you to know about that is that both tails point up, or if it's a negative x to an even number, then in that case, both tails point down. So when we talk about end behavior, we're talking about the first term in the polynomial. Not any of the intermediary terms, they don't matter. Just the first term, the leading term, tells you the end behavior. And if it's an even power, it's either a parabola facing up or it's a parabola facing down. You don't technically use the word parabola anymore. Parabola only refers to x squared. In this case, what you would do is just refer to it as an even power function. An even power function. What's the end behavior? An even power function. You could say it's parabola-like, or you could call it parabolic. Okay, so now what if the power is odd? So here's the first odd power, x to the 1, and then x to the 3, x to the 5, x to the 7, to the 9, to the 11, to the 13th. Ooh, oh, that was 113th. To the 13th, to the 15th, to the 17th. So what do odd exponents look like? Yeah, well, it has the side to the right is pointing up, and then the side to the left is pointing down. Going back to x cubed, which is the most fundamental, x cubed, you'll notice it basically looks like a parabola. Like if you just look at the right-hand side, it looks like a parabola facing up. And if you just look at the left-hand side, it looks like a parabola facing down. And that's the nature of an odd function. So any x to the odd number, so if that's the leading term, x to the odd number, you're going to have what I call, this is what I say, maybe I'm becoming silly, a smiley face to the right and a frowning face to the left. That's how I think about it. It's just called a cubic. This is what a cubic function looks like. Not just cubic, but any odd-powered polynomial. So x to an odd polynomial looks like this, and if I put a negative sign in front of it, that flips it upside down. And so now, the smiley face to the right becomes a frowning face to the right. And this frowning face to the left becomes a smiley face to the right. These four graphs right here are what we call end behavior. And you get to end behavior by just looking at the first term in the polynomial. Or you don't even have to multiply the polynomial together. You get the end behavior by noticing how many factors there are. So like in this problem, how many factors do I have? I've got 1, 2, 3, 4, 5. So I automatically know this is going to be an x to the 5th polynomial, which tells me it's an odd behavior, which tells me that it's going to look like that. Right? So that's end behavior. So really, we know a lot. We know a lot about this thing. Take a look at this one. I can already graph this thing completely. I now have total knowledge of this graph. I could make myself a graph and say, well, first of all, I know where all my x-intercepts are. They're at negative 1, 2, 3, 4, 5, 6, 7, 8. And then I also, at negative 3, 1, 2, 3. And I have x-intercept at 1 and at 1, 2, 4. Okay, so those are my x-intercepts. I knew that my y-intercept was 5, so 1, 2, 3, 4, 5. Okay, so far that's what I have. I got my x-intercepts, my y-intercept, and I know my end behavior is x to the 5th, which means leaving my last x-intercept, it's got to go up like this, and leaving my first x-intercept, it's got to come down like this. Right, because x to the 5th, generally speaking, looks like that. And so now, the last thing you do is connect the dots. You connect them with a nice little swoopy line, and you say, well, it must cut through there, and down, and up, that point, down, up. And you would look at that, and you'd say, boy, that's a good-looking graph. That's a real nice-looking graph. You know, if we're doing it off the top of your head, without actually looking at a graph. Now, I'd like to show you that that's correct. If I type in the function x plus 5 times x minus 4 times x plus 8 times x minus 1 times x plus 3. Whoops, that was a capital X. That was still a capital X. There we go. And I'm going to zoom out, and I need to change my scale quite a bit. My y-axis, we went down 200. There we go. And then up 300. Not big enough. How about 500? How about 900? Oh, that's looking better. And then how about I'll go down to 400? So you have to play around a little bit with your scale. Hold on. I'm going to go all the way down to 1,000. Or 2,000. No, yeah, I'll make it 1,500. All right, now we're talking. And then all the way up to 1,200. All right. Is that what my graph looks like? You know, roughly speaking. I know that I didn't nail it, right? But my graph does start out down here. Then it goes up through -7, -8. Then it goes up. Then it comes back down to -5. Then it goes back up to -3. And I go up and I touch somewhere around there, which, well, I put it as 5. But That's because I just made up the top function. And actually, there's my y-intercept there. Then it comes down again, and then it goes back up. So what did we just accomplish? We made a fairly good hand sketch. That's what we just accomplished. We made a fairly good hand sketch, which has all the key characteristics of what the actual graph looks like. And that's your ultimate end goal for the next couple of weeks, is to take any polynomial and then make a hand sketch that includes all of the x-intercepts and the y-intercept. Okay, so everybody, you go ahead and try it. Here's a couple of polynomials that are already factored for us, which is a huge gift. Because factoring is the hard part. If you already have it factored, you've got an easy job of it, because you just look and see where the x-intercepts are. So I'll do the first one with you, and then you do the second one. We have f of x equals x minus 6 times x minus 2, and then x plus 1, and then x plus 4. So I'm going to now call on some people here. What's my first x-intercept? Isaac? Yeah, just regular 6. And my second x-intercept? Josh? 2. Yeah. And then my third x-intercept? Syra?
1.
Negative 1, very good. And then my next x-intercept, Urban? Negative 4. Now, here's another trickier question. Let's say I go ahead and FOIL all that together. What would my first term be? Yeah, if I FOIL all this together, I don't actually know what it all would be, but I know the first term would be x to the 4th, and then plus a whole bunch of terms. And then what would my last term be? My last term would be negative 6 times negative 2 times 1 times 4, which you could just type into your calculator. So let's see, 6 times 2 is 12, times 1 is 12, times 4 is 48. And it's a negative times a negative, which is positive, times positive times positive. So yeah, 48. So now that's kind of fun. We call that lazy foiling. Like, we foiled it, but we didn't bother to write down what any of the middle terms would be. But we know for sure that the first term is x to the 4th and the last term is 48. So now what does this tell us? The x to the 4th tells us the end behavior. So now I know immediately that since this is a positive x to the 4th, it's a positive parabolic graph. And then my last term there is my y-intercept. And now you have all the information you need to make a sketch. So the sketch that you're all about to make is what I call a restaurant napkin sketch. You've all been at a restaurant with a friend and you're like, man, we got to do some math. And then you ask the waiter or waitress to bring you a pen, and then you use the napkin and you start doing math on the napkin. You all know what I'm talking about. You've been there. So that's what I'd like you to do is you're just drawing a graph that is good enough for the sake of a polite conversation at a restaurant. So on your napkin, you jot down a graph, and then you say, okay, my x-intercepts are 1, 2, 3, 4, 5, 6, and then 2, and then negative 1, 2, 3, 4, negative 4. And then your y-intercept, because we're all friends, you just make a tick mark, you call it 48. You notice you're not trying to make it to scale. You're not sitting there going tick, 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 up to 48. There's no need for that at a restaurant. And then we need end behavior. So the end behavior means you look at the 2 x-intercepts on the farthest outside, and you say, well, my tails are going to be pointing up. So I know now that that tail is going up, and this tail is going up. And then at that point, you connect the dots. And you've now produced a high-quality restaurant napkin sketch that you could use as a conversation piece when you're out to dinner with a friend. And you just connect the dots. There's your graph. Have any of you ever asked a waiter or waitress for a pen because you got to draw something or write something? I do all the time. All right. Yeah, it is really helpful when it's actual good paper. I've never written on a cloth napkin. That would just be rude, right? You don't write math on a cloth napkin. Okay, so now everybody do your own. The second one, do f of x equals x minus 4, x minus 1, x plus 3. Make yourself a nice sketch of what that graph would look like.
That's really you just took it. Yeah, I use it.
And yeah, no, that's a great idea. And you know I'm recording. So you can always
So this, I was just gonna say, because sometimes if you're thinking of the cash draw.
Well, that's true, yeah, if I'm over there.
On the side, so.
Well, that's a good point. Yeah, so that's great. Okay, so everyone want to compare your answers? So first of all, you know you have 3 factors, so you know you're going to have or 3 x-intercepts. And the x-intercepts, I'm going to write them out. I always write them out instead of just looking. So I know that it's going to be 4, 1, and -3. I go -1, 2, 3. There's an x-intercept at 1, and then a 2, 3, 4. That's what I have so far. And then if I did FOIL that out, I would have f of x equals, the first term would be x cubed, and then the last term would be the product of -4 times -1, which is +4 times +3, which is +12. So there you go, some lazy person's foiling. Skip all the middle terms. And so now I know my my y-intercept will be up at 12. And so now I got a bunch of dots. My end behavior is x cubed. And so my end behavior would look something like half face to the right, front face to the left. And so I put a tail, leaving the last x-intercept on the right going up, the last x-intercept on the left going down. And now you just connect the dots. So from this dot, I would go up, and then through, and then through. Well, it's -4 times -1, which is +4, times +3, which, yeah. I am multiplying the factors. Reason being that when I actually do FOIL, I would be multiplying them. Now, that's a really good point. If I multiply the x-intercepts, that would be -12, which would not be the y-intercept. So that's a very good and subtle point. To find the y-intercept is the result of FOILing, which means you're actually multiplying the numbers that you're given. I don't know of anything that comes from multiplying the x-intercepts together. Yeah, I don't know what that would give you. It would be a number. Yeah, it just wouldn't represent the y-intercept. Okay, so there's our graph. Now, of course, if you really wanted to, what could you do to check the work and feel confident? You could graph it. So I'll come on over here, and my function was x minus 4, x minus 1, x plus 3, and boy, I zoomed out a lot, but there you can see my graph. It is as we suggested, and I'll zoom in there. My y-intercept is indeed 12, so that settles it. And I've got my x-intercept at -3, and at 1, and 4. Okay. How does everyone feel about this? My hope is that, right, oh yes, Abe.
Is there a way we can check on the graphing calculator, something like that?
Yes, of course. On your graphing calculator, you just type in the factored form itself. So you would, I already moved the screen. You would type in to your y1 equals exactly that. So when you go to y equals on your calculator, you would just type in parenthesis, x minus 4, parenthesis, parenthesis. You type it in exactly it is, and then you'll get a graph. You'll probably have to change your window quite a bit to get the whole graph to fit on your window. But yeah, absolutely. You can check every problem in here by using your graphing calculator. Okay, so the next section is write a polynomial function that has the given zeros. And I say sketch a graph. And note, we are essentially saying that writing a function as a product of binomial factors is a way of listing and creating x-intercepts. So let me see here. I think I'm done with that problem. I'll take this space. So, like for instance, in this first problem, number 5, I'm saying that I want my x-intercepts to be 1, 4, and 5. Now notice, this is really interesting what we're doing here. We're saying, draw me a, not just draw me, find a function that has the x-intercepts 1, 2, 3, 4, and 5. Find me a function that looks like that. The remarkable thing is, there's actually many ways that I could draw a graph to look like that. So I'd like to, share at least a couple with you. Let's say that I have these x-intercepts, and I want to demonstrate the diversity of ways that you could actually generate a function that has those x-intercepts. And think about it in your own mind. How could I draw a continuous line to go through those 3 points? I could draw it like this, up, down, up. I could start up and go down, up, down. I could go bounce, bounce, bounce. Right? So there's a lot of different ways that you could create a function that has particular x-intercepts. So is there one answer to this problem? No, there's not one answer. I would suggest there's lots and lots of different answers. I mean, how many total ways could I actually do this? Like, for instance, right now, folks, let's all agree, I'm going to call that a slice. This is a slice because I started up top, I sliced through it, and came down to the bottom. So it could be slice, 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 or it could be slice, slice, slice. Whereas this, I'm calling it bounce, and I went bounce, bounce, bounce. So consider each x-intercept could either be a bounce or a slice. So how many different possible graphs could I actually draw here? Well, how many? Not quite. Well, okay, yeah, that's true. Infinitely many. But like, for instance, I could end up with a bounce, and then a slice, and then a bounce. Right? I don't mean to confuse the situation by suggesting there's so many different ways that you could draw a graph. But there are so many ways that you could draw a graph, given those first 3 x-intercepts. So when they say, write a polynomial function that has these zeros, we're going to write the simplest function that can have those 3 zeros. And that you get by simply writing out f of x equals x minus, x minus, x minus, and you just plug in those numbers. Because that's how it works. You can set up and create a simple function, the simplest polynomial there is, that will have those x-intercepts by setting yourself up with x minus, x minus, x minus, and then you just write in the x-intercepts. And this now creates the quote-unquote simplest polynomial there is, which means that each x-intercept will be a slice. So we're creating a polynomial where each x-intercept, each x-int is a slice, as in not a bounce. And the end behavior is a positive end behavior. Because as you know, once I FOIL this whole thing out, I'm really going to have the function x cubed. So that's a positive x cubed. And then my last term will simply be the product of all those all the numbers inside the factors now. So -1 times -4 is +4, times -5 is -20. And so this is also the simplest function that has those x-intercepts because we're saying it's positive behavior, and the y-intercept is what you'd expect by just multiplying the numbers inside the factors. Notice that was very subtle. If I multiplied 1 times 4 times 5, it'd be +20. But again, we don't multiply x-intercepts to get anything. We multiply the numbers inside the factors because that's the result of FOIL. Okay, so in any case, what's the answer to this problem? Write a polynomial function that has the given zeros. Sketch a graph, it would be this one. This is the graph we just did. It's the simplest possibility. Not all these like slice, bounce, bounce, bounce possibilities, but simply the slice, slice, slice possibility. Questions? Let's try the next one. The next one's a little more interesting because there's a negative number. So at number 6, again, you can write down the x-intercepts first. It's always a good idea to write down problems in your own handwriting. So 5, -5, and 1. And then set yourself up by writing your function empty. You write a factored polynomial empty by writing x minus, x minus, x minus. That's the empty form of a factored polynomial. And then what you do is you drop in your x-intercepts. So one of my x-intercepts is 5, the other one is -5, which you'll notice leads to a double negative, so that'll become positive. And then my last one is just a 1. Now, I wouldn't give that to somebody with a double negative. That's not very clean. So I would say my answer is x minus 5, x plus 5, x minus 1. Because you don't want to have a double negative in there. So now what can you actually say? Instead of setting it up as x minus, x minus, x minus, what are you really doing? You take your x-intercepts and then you do what to each of the signs? You just change the signs. So just like before, when you use the zero product rule to solve each of those, you knew to just take the opposite sign, and that gave you the x-intercepts. Well, likewise, when you put the x-intercepts in, you can just change all the signs. And that's a very valuable thing to note, is that the sign of the x-intercepts and the sign inside the factor are always opposite. Opposite signs. That's a nice generalization. So whatever your x-intercepts are, you change all those signs, and then it's in factored form. And if it's in factored form, you change all the signs, and then they're x-intercepts. Okay, but we're not done here. It still says sketch a graph. So when we talk about the ability to sketch a graph, we are looking at what 3 pieces of information. When you make a graph, what are the 3 things you need to do, and in what order? So on my graph, what's the first thing I'm going to list? The most interesting thing, the x-intercepts. So that's what they gave me in the first place. So 1, 2, 3, 4, 5 is one of them. Negative 1, 2, 3, 4, 5 is another one of them, and then at 1. So first you list out your x-intercepts, which in general is what you have to work the hardest to find. Next, you would list out your y-intercept, which in this particular case, we have to multiply to find it. So negative 5 times 5 is negative 25, times negative 1 is positive 25. So now I know my y-intercept is positive 25. Again, you don't have to draw it to scale with all the tick, 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 tick. You can just put 25 there. The x-intercepts you have to draw to scale. Let's be clear. This isn't anarchy. Okay, so the x-intercepts, you definitely need tick marks. Whereas the y-intercept is probably going to be some big or small number. So you can just put a tick mark. And then finally, the last thing you do, end behavior. So what is our end behavior? It's 3 factors, so it's x cubed. And in fact, it wouldn't hurt to go ahead and write it out. This is f of x equals x cubed plus dot, 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 plus 25. Right? That's what it would look like if I FOILed it out. So my end behavior is smiley face to the right, right face to the left. So I'm going to put in from the furthest right hand x-intercept, the tail going up. From the furthest left hand x-intercept, the tail going down. Then if you really wanted to say the last thing you do is connect the dots. With a nice swoopy. That's the technical term, a swoopy. You draw a swoopy. So slice, slice, slice. I know it's early. You're all so quiet. Does anyone have any thoughts or questions? Is all of this coming in just fine? You're like, okay, yeah, sure, this is basic. Sure. Yeah, wait, number 5? Oh yeah, sure. Well, I did. Yeah, 1, 4, 5. I didn't break it down into those same steps. I just made a quick step. Now, let's do either 7 or 8. How about we do 8? 8's a great one because you have a positive number, a negative number, and you have a 0. So what would that look like? So, starting with number 8, we know that our x-intercepts are -2, 0, and 2. And therefore, my function, f of x, is, I'll go ahead and do the change the sign trick. So -2 becomes x plus 2. 0, well, you don't change the sign on 0. It's just x plus 0, right? Or you could write x minus 0. Does it matter if you write x plus 0 or x minus 0? No. And in fact, do we even need to write plus 0? We don't even have to write plus 0. We can just write x. And then change the sign to positive 2. That's x minus 2. So that's what our factored form would look like. And then if you went ahead and FOILed it all together, you know the first term would be x cubed, and then plus dot, 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 dot. What would the last term be? Yeah, maybe keeping that 0 there is helpful after all, because you have to multiply all these numbers together. And 2 times 0 times -2 is automatically 0. So our last term is actually 0. So now we can go through and do everything we need to do to make a graph. So I said the first thing is to do your x-intercept. So you have an x-intercept at -2, at 0, and a positive 2. You've got a y-intercept at 0. Notice I already have my y-intercept there. Because there was a dot on the x-axis at 0, that's automatically the y-intercept as well. And then end behavior, so this is a cubic, so it's going to go up to the right and down to the left. And then you just go slice, slice, slice. In the beginning, it's always slice, slice, slice. It's only towards the end of this unit that we start talking about bouncing off of an x-intercept. So we go slice, slice, slice.
So you always are gonna reorder the numbers to be like -2, 0, 2.
Well, oh, right, because I reordered them?
Yeah.
Well, you know what? I haven't been very consistent up here today. I prefer to always write my x-intercepts in order, like they're on a number line. So here I did it correctly, right? Like on a number line, it'd be -2, 0, 2, because that's what's going to show up on my graph. Right, on my graph, my x-intercepts are -2, 0, 2. So I would want to write my x-intercepts in order from left to right. But then again, in the function itself, I mean, it really doesn't matter what order you write them in. But just as a personal rule, I try to write my x-intercepts in order. Yeah, did I answer your question, Gabe? Okay. All right. So I have more problems there, but I think we've covered the concept. So, you know, you could do more or not. This is just a practice packet for us to get the main idea. So let's see here. And then I have more. There's more in this packet, right? Yeah, there is. That's right, because we're doing a high-level overview of the whole process. Oh, this is so exciting. Okay, what I think we'll do, since my phone just went off, let's just take a break. So time is 9:02. Let's all come back at 9:12.
I don't know. Well, because he had it on there, and it was like negative. Oh, mine will be negative 9. Here's that.
Wonderful. You're multiplying by positive constant, so it has to be a negative. To be a negative and a negative. Yeah, that would be. Yeah, inside the factors would be x minus and x minus, which means that your answers would be positive and positive. No, the 3 and the 9 are just x-intercepts. So if you drew a picture real quick, the x-intercepts are 3 and 9. And you can make a quick sketch, just like we're doing. So now, so make your problem. Using the exact same idea we're doing right now, but it's bad. And it's, you know, it's a square, so there's your sketch. And now where's your minimum? Back there. That's the minimum. See, this function represents your cost. And so they're saying how many pencils should you produce to minimize the cost. So this y-axis is cost, right? Cost. Whereas the x-axis is the number of pencils. So they're asking what's the minimum cost. So the minimum is right there, put a dot at the vertex. So we're interested in that one. Yeah. And then you plug that back into the function to find what the actual minimum cost is. Well, that's Oh wait, no, it could be negative 9. Yes, you're right. It makes no sense. The fact that it turned out to be negative was silly.
That's,
It's a bad function.
so confused.
But yeah, that's why we would use this fact that it turned out to be negative. Not
6,000.
yes, that costs negative 9. By the way, super fun periodic tables.
Yeah.
Oh my gosh, this is so fun. Do you have all of them in there? Boron,
No.
oh my gosh,
I have
iron,
to memorize some of them.
hydrogen, helium. Oh, so excited.
130. You need to take my teacher, she's awesome. Yeah. But hold on, I don't remember what her first name is, and her last name is Colin, she's really young. She's just really cool, I don't know. She's kind of awkward to talk to, like, individually, but she's not. I just feel like it's awkward every time I have to, like, try and talk to her. But she breaks everything down. Really helpful.
Okay.
Oh, I'm just getting my associate's of arts and I'm actually graduating in May, so I can go to ASU. My end goal though is to be a forensic pathologist assistant. For like the same. Fair enough. Hopefully. He's obsessed with you. I know, but he's obsessed. So like, he just sent me this picture. It's just. You know what I mean? I'm gonna get a better picture of her face. Oh, yes, good man. Oh, she did. It's way different. I still have it. I still have it on my secret.
That one broke. I remember
Yeah, my secret Nintendo from like my childhood is still alive. And I have it. So we must out. It says not even blow on the by the way. I know.
Like you order. Yeah, I ordered. Yeah. And then they get. You like the yeah. I didn't know that every day. And just like, I'm like, I don't know if I want to do that. Because sometimes I really just like, and then, the other day when I did all of them were $170 more. So you're paying $70. And I was trying to see
All right, folks, let's keep going. So, let's talk about definitions. Are we on the next page now? Yeah, there we go. So, polynomials. What's the etymology of the word polynomial? What does poly mean? Yeah, many. Maybe you know poly from, like, say, polytheistic, many gods, or polyhedra, like a cube, or what are some other poly words? Polygamy? Many partners? Any other polys? Poly what? Polykinetic?
No.
Oh, polytechnic. Yeah, what does that mean? Oh, okay. Yeah, so poly means many. And what's nomial? What does nomial mean? It could mean number. That sounds pretty close. It means name. If you look it up in the original Latin, it's many names. And many names is a bit of a misnomer. A polynomial is really many terms. So even though nomial means name, a better word for it is term. So a polynomial is a mathematical expression with multiple terms. So like the term x to the fifth, and the term x to the fourth, and the term x cubed, and the term 0x squared, and the term 0x1, and the term 5. Basically, many terms mean a whole bunch of things being added together. That's what a polynomial is. A polynomial is a something plus a something plus a something plus a something plus a something. They're all connected by plus or minus. So it could be a term plus or minus another term plus or minus another term. That's what we're talking about with a polynomial. So you could jot down a polynomial is fundamentally an addition problem, right? A polynomial is a bunch of things being added and subtracted together. So here are some examples. Oh yeah, so does a polynomial is a mathematical expression with many terms. So some examples. If you just want to think about what a monomial is, so a monomial would be just a single term. So it could be just the number 5, or just the number 3x, or just the number 4x squared. Okay? It's just a single term and that's it. There's nothing else with it. Whereas what would a binomial be? So mono, of course, means just one. And then binomial, bi means 2. So that could be something like 5 plus 3x, or x squared minus 8, or x cubed minus 1. Those are all binomials because you have 2 terms. It could also be x cubed minus x squared. In every one of those cases, you have 2 terms that cannot be combined together, right? A binomial would not be like, so not 6x minus 3x. That's not technically a binomial because you could combine those like terms, and 6x minus 3x is really just 3x, and so that's a monomial. And so it has to be, a binomial is 2 terms that cannot be combined. Likewise for a trinomial, the most basic trinomial that we know is ax squared plus bx plus c. Right? Because you have 3 terms and they can't be further compressed and combined. Now, basically, we just use the vocabulary monomial, binomial, trinomial, polynomial. It's really funny that in math we just go 1, 2, 3, many. Right? So even though if you did have a 4-termed polynomial, you could be cute about it and say a quadrinomial. Quadrinomial. Just like you'd say a quadrilateral is a four-sided shape, you could refer to a quadrinomial. And you'd have ax squared, or no, ax to the third plus bx squared plus cx plus b. And that would definitely make you really cool at a party. If you walked up and you're like, hey, everybody, look at that quadrinomial. Because anyone else would just call it a polynomial. But you could call it a quadrinomial. What would you call a five-termed polynomial? A pentanomial, like a pentagon, pentanomial. And six terms? A hexanomial. Again, nobody does that. Nobody says quadrinomial, pentanomial, hexanomial, decanomial. You just say polynomial. So anything more than tri, you just say polynomial. So a polynomial is any polynomial with four terms or more, because otherwise you'd say, hey, look at that trinomial, look at that binomial. Okay, so that's just some vocabulary for us to be all familiar with. Name each polynomial by degree and the number of terms. So let's all know the word degree. The word degree simply refers to the highest power of x. So here the highest power of x is 3, here the highest power of x is 5, here the highest power of x is 6, here the highest power of x is 3. So that's the degree. The degree, you'll note, tells you the end behavior. So the degree is the highest power of x, which is the end behavior. If you just circle the word degree and jot that down, degree is, oh, I even have in parentheses already, the highest power of x. But it also tells you the end behavior. And then, so how many terms do we have? Well, that's a monomial, that's a binomial, that's a trinomial. That would be just a polynomial, polynomial. You don't bother getting any more specific. So right now we're just building vocabulary. We're building vocabulary about how to talk about these things. You'll notice that the degree is not automatically the nomial name. So like here, the degree is 3, which means how many x-intercepts could you have? At most 3. You could have less than 3 x-intercepts, but at most you have 3 x-intercepts. So this is degree 3, but it's a polynomial with, well, a quadrinomial. There's 4 terms, but the degree is 3. Okay, so just a couple quick thoughts, and we're just going to do a couple of these. What if you had to add a couple polynomials together? How would you do that? So, for instance, we'll just do for 18. So I have 4r minus 8r cubed minus 3 plus 5r to the fourth, and then plus 6r to the fourth plus 7r minus 2 minus 5r cubed. How would you add these together? That's good? You just combine like terms, right? Because we're adding, you can just pretty much ignore the parentheses. You just got one long string of terms being added, and then you just combine like terms. I like to use a separate symbol. So I go through and I say first, what's my highest power? R to the fourth. So the first thing I do is combine my r to the fourth, so I have 11 r to the fourth. My next highest power is r cubed. So now I'll use a squiggle line. Say, okay, there's my r cubed terms. So negative 8r cubed minus 5r cubed is minus 13r cubed. And then next I look for the next highest power, which is just r. So maybe this one I will I don't know, circle the r terms. So I've got a 4r plus 7r, that's 11r. And then finally, I've got my just numbers. So maybe I'll put a box around those. So negative 3, negative 2, that's negative 5. So you just combine like terms, and you just want to be really, really careful. What if you want to subtract a couple of polynomials? So that was number 18. What if you want to subtract a couple of polynomials like number 20? So now you have 5 minus 2x minus 2x squared minus 3x to the fourth. And then you're going to subtract the polynomial 6x squared minus 7x plus 2x to the fourth minus 1. What do you have to do with that minus? You have to distribute. Now keep in mind, distributing, what does that really mean? To distribute a negative means you're going to do what to all those signs? You're just going to change them all, right? So you can either draw a little arrow that says, okay, I'm going to distribute the negative, or you can just change it to a plus and then change all the signs. So negative, plus, negative, plus. Now you notice we're not doing all these problems. I put a selection of problems up just to have something to talk about. So then you would combine like terms just like you did. So it's adding polynomials. What about multiplying polynomials? We haven't specifically talked about FOIL in class. We've done it. We haven't necessarily talked about it. So in number 22, how would you FOIL 8k plus 5, and 8k minus 8. So first of all, what does FOIL stand for? Yeah, it stands for first, outer, inner, last. So what I typically like to do is I make my lines for first and outer on top, and then my lines for inner and last on bottom. So first, 8k times 8k. What is 8k times 8k? Yeah, 64k squared. It's 8 times 8 is 64. K times k is k squared. So I have 84k squared. So that was outer. Sorry, first, and then outer. 8k times negative 8 is negative. I wrote 84. There we go. 8k times negative 8 is minus 64k. And then I do my inner on bottom. So inner, 5 times 8k is 40k. And then last, 5 times negative 8 is minus 4. So this FOIL, and then what do you have to do? Then we combine like terms in the middle. So we end up with 64k squared minus 24k minus 4. So that's FOIL. We're basically just reviewing all the different concepts that are playing in to the skills that we're building for chapter 3. Okay. So now we're about to do something really fun. Now, first of all, I would like a poll. So really do, please raise your hands. If you remember doing synthetic division. 1, maybe 2. It was a confusing question because I said raise your hand, 2 people raised their hand, but I saw 6 people show a face of disgust. Does that mean you do remember it? No? Okay, well, so synthetic division is actually really cool. I don't know what experience you had with it when you were younger, but synthetic division is a really, really cool tool. And so I'm excited to share it with you and show you how to use it. So what we're about to do now is we've already covered all the high-level concepts of everything we're doing in chapter 3, right? So everything we're doing in chapter 3, you take a polynomial, you factor it, you find the x-intercepts, the y-intercept, the end behavior, you graph it. That's the high-level concept. What we haven't done now is actually talk about how do I actually go from here to here. Because once you're here, you're done. Like once you're factored, it's so easy to make a sketch. You know, you just do it. But going from here to here is the challenging part. It takes a lot of effort, which is how we'll spend most of our time in chapter 3. Is knowing how do you go from the addition problem polynomial to the factored version of polynomial. That's the tricky part. I won't call it hard. This is tricky. It takes more time. So in order to do it, you use something called synthetic division. And so I'm going to first just demonstrate for all of us, and we'll do it all together. We'll do a lot of this together. How to do synthetic division and what synthetic division actually does. So is everybody here on this page? It says Introduction to Synthetic Division and how amazing it is. You know that I wrote these worksheets, right? Like throwing in something like how amazing it is. That was my editing. All right, so we've got this first function. So everyone, let's look at it. You don't have to write it because it's already there. But f of x equals 3x to the 4th minus 6x cubed minus 5x squared plus 12x minus 1. And what I want to know is, I want to evaluate that function at x equals 2. So essentially what we're going to do is just plug in x equals 2. Okay? Now before we even plug that in, let's look at what we already know. What do we know? If I said sketch a graph right now, sketch a graph with as much detail as you possibly can, what could we graph for sure? That's our y-intercept. The last term is always a y-intercept, so give yourself a little thought. And what else do we know for sure? The end behavior is a 4th power, which makes it parabolic. It's a 3, but it's positive, so it's facing up. So all I know now for sure is that I got 2 tails pointing up, and I got a y-intercept at -1. It's not much. You know, there's a lot left to fill in. And what left is there to fill in? The x-intercepts, and essentially the wiggles. Not the hot singing group for kids, the wiggles. But you know whatever is left down there is going to be just some x-intercepts, and you wiggle it around, and then you're done, right? So, I mean, you know, not bad. We're on our way to having a sketch. But we need to find those x-intercepts. So One thing that you can always do with a function, remember there's two things you can do with a function, plug something in or set it equal to something. And what we really want to do is set the whole thing equal to 0 because that'll tell us all the x-intercepts. But the other thing you can do is plug a number in. So what if I wanted to find f of 2? What would you have to do technically? You'd have to plug 2 into all that, right? Now who wants to do that? That would be 3 times 2 to the 4th minus 6 times 2 cubed minus 5 times 2 squared plus 12 times 2 minus 1. Now everyone go ahead and calculate that in your head. No, nobody wants to. Everybody go ahead and calculate that on your calculator. Maybe you still don't want to, right? Because look at all the work that's involved. You have to sit there on your calculator and write 3 times 2 to the 4th minus 6 times 2 cubed minus 5 times 2 squared plus 12 times 2 minus 1. It takes a little bit of time, but go ahead and do it. Type it all in your calculator, everybody. Actually compute all of that. And keep in mind what we're doing now is we're doing an input, and you're all about to calculate the output. So, did anybody else get 3? Oh, goody go. Yes. Okay, so what does this mean? My input was 2, my output was 3. What does that mean? What do I know about my input 2, output 3? This is a coordinate. And so now I know that I have the coordinate 2, 3 on my graph. How does that help me over here? Well, 1, 2, 1, 2, 3. I've refined my graph a little bit, haven't I? I've got one more teeny little piece of information. I know that I've got that coordinate on my graph, and so I shifted my tail to go above it because I know that it has to go through that point. Okay, well, that's what I know so far. And plugging a number in is not very exciting. Because now just imagine if I wanted to get the rest of the graph, I would just have to do a table of values with maybe, say, 10 values. And if I did 10 values, maybe I'd get enough points to kind of get an idea of what's happening. So like if I did enough table of values, I could put all those together and say, oh, it looks like that, right? It'd be pretty laborious to sit there and do a table of values. But if I did a table of values, I'd eventually get enough dots that I could connect the dots and know what it looks like. That still wouldn't tell me the x-intercepts very precisely. I'd still be wondering, where does that go through? Where does that go through? Right? So this whole input-output method is very limited in terms of what we can do, and time-consuming because you have to type it all in. Okay, so now let's see what synthetic division does for us. So cool. Everybody, I want you to set up your work just like me. So first of all, is our polynomial written in descending orders of powers, x to the 4, 3, 2, 1, no x? Yes. Now take all the coefficients, and we're going to write them down in a straight line, just the coefficients, 3, -6, -5, 12, -1. And you're going to draw a little kind of box shape underneath it.
I like it.
Oh, good. Yeah, I mean, it's a good procedure. The procedure itself is very simple and straightforward. So, and now what we're doing is I want to plug the input of 2. My input is 2, so I literally write 2. That's my input. That's my input. I'm going to input 2 into this procedure called synthetic division. So here's how the procedure works. And I recommend using your left hand to kind of help you out. You begin the procedure by dropping the first number, whatever it is. You drop the first number, whatever it is. And then what you're going to do is go through a alternating process of multiply, add, multiply, add, multiply, add. So here we go. You always multiply by this number, your input. So 3 times 2, multiply, 6, add, 0. Now, multiply, 0 times 2, 0, add, -5 is 0. Again, multiply, -5 times 2 is -10, add, 2. And then multiply, 2 times 2 is 4, and then add, 3. What do you notice about the number 3? That's the output. So what do we have here? This process called synthetic division. This is your input, this is your output, and therefore 2 and 3 make a coordinate. So that's all synthetic division is. Synthetic division is simply a tool for finding your input, or turning an input into an output. You'll notice that this procedure is easier than computing powers. Like, let's say that my input was even slightly larger such as the input of the number 7. Okay, so 7, 3, -6. Now this might bite me. It's not a good number. But first of all, if I plug 7 into that original problem, notice that I'd have to do 7 to the 4th. First of all, nobody's doing that in their head. And it's going to become a very large number. Like 7 to the 4th, super big, times 3. These numbers get really big really quick. Whereas with synthetic division, let's do it again. Drop the first number, multiply, add. Multiply, add. Multiply, add. Okay, this one did get big. 7 12 times 7. Not sure what that is. Multiply. 4, 9, 4, and then add 4, 9, 8, 3. Okay, so there we go. I have a new input output, and I know that my coordinate now is 7, 49, 3. All right, so that's how the procedure works, and it's so much better to do synthetic division than to actually try to plug it in, at least by hand. You know, again, pretend you have to do this by hand. Then the numbers typically stay smaller longer than if you did all of those terms up there by hand and actually raising 7 to the 4th power, 7 to the 3rd power, and so on. Okay, so that's how synthetic division works. Let's try a negative number. So, folks, we're going to get used to starting a synthetic division from the coefficients and just running with it. So let everyone look at number 28. Just take the coefficients. Now, first you have to check, are the exponents in order? 4, 3, 2, 1, no n. So yes, the exponents are in order. So now let's take the coefficients. That's 1n to the 4th, -1n cubed, -28n squared, +13n, and 5. And we're going to plug in the number -5. So if you just want to do this on your own now, if you remember the whole multiply add procedure, you can just do it. If you want to follow along with me and watch again, it's this repetitive procedure where I find it very helpful to actually say multiply, add, like Grover when he says near, near. Anybody? Sesame Street? No? Okay. So drop the first term. Now multiply, add, multiply, add, multiply, add. Multiply, add. So got my input, got my output. I now know that the coordinate -5, -10 is all I got. Now you notice this is a lot of positives and negatives work that you're doing here. So if you feel very comfortable with multiplying negatives and adding, subtracting negatives, great. You can just do it all in your head. But if you feel, oh geez, I really need to double check that, I would be double checking your work as you go with the calculator to make sure that you're multiplying your negatives correctly and adding your positive and negatives correctly, because you've got so many opportunities to make some mistakes here. So just know, if you feel a little shaky about your positives and negatives, that's fine. Just use your calculator. You're allowed to use your calculator in the course. There's no harm in doing that. Okay, well that's it. Everybody go ahead and bust through 27 and 29. Make sure that you check the polynomial first. Powers of n to the 4, 3, 2, 1, no n. Powers of a, 4, 3, 2, 1, no a. Those are good to go. You write the coefficients in order. It's really important that you get those signs correct. So the coefficients for number 27 is +1, -10, +31, -36, +37. If I were you, I would start a ritual of actually saying positive and negative every time. And then what are we plugging in? 5. So there's number 27. And then in number 29, -3, 6, 3, 30. There. Okay. 6. All right. So yeah, this procedure called synthetic division, which has a whole lot more information in it than just the input output. There's a whole other row of numbers along the bottom, and that other row of numbers along the bottom actually does have more information for us. But the last number, that's our output. And And that's the first and most fundamental way to use synthetic division. It's just doing input output. It's not just the last number that's important, we need all of them. And your calculator won't tell you those. Only the two. All right, so if you want to check your work, the first one, number 27, so drop the number, multiply, add, multiply, add, multiply, add, multiply, add. Did anyone else get 7? 7? Oh, goody. Okay, then drop the first number, multiply, add, multiply, add, multiply, add, multiply. Did anyone else get 12? Okay. So now, again, all we're doing right now is generating coordinates. We're generating coordinates that we know are on that polynomial, 5, 7, or this time the coordinate -6, 12. The thing is, these coordinates that we're generating are incredibly uninteresting because they're not x-intercepts and they're not y-intercepts. So if I wanted to find an x-intercept, first of all, what does the coordinate for an x-intercept look like? Like, what could that coordinate be? Just pick a number. 4, 0. Input 4, output 0. So if I have an x-intercept, my output better be 0. So here's what we really want, and what we're going to really pay attention to is ideally, when I do synthetic division, I want to input a number, whatever number, I want my output to be 0. That's what I'm really looking for. Because anytime I do input, output, and that last number is a 0, I just found an x-intercept, right? Because if I input 5, output 0, that's the coordinate 5, 0, and I'm going to plot that on the graph, that's an x-intercept. So getting a 0 there as the last number is so important and so special and so exciting. We'll put a smiley face in it. Because that's going to remind us that we just found an x-intercept. So anytime you do input, you do the whole procedure, and you get a 0, bam, you just found an x-intercept, which is super exciting. Because not only did I just find an x-intercept, but that means that I can begin writing the factored form of my polynomial. Because if my x-intercept is 5, what can I write down now? X minus 5. I now just found one of my factors, right? So the whole idea is I started with a polynomial in addition form, but I want to turn this thing into factored form, right? That's my whole goal. I want to take a polynomial that's in addition form, and I want to turn it into factored form. So if I take my polynomial and I do synthetic division, and I get a 0 as my output, I just found an x-intercept, and now I know one of my factors. I still have to find the other factors, but I just found one. So everybody, our goal is to do synthetic division and get a 0. Okay, so that's synthetic division. That's the first thought. Now, let's move along here. What's that? The number that you get at the end is, yes, you can refer to that as the remainder. That is true. You can refer to that as the remainder. There are a lot of different ways that you can refer to that last number. The first way I want us to refer to it is the output of the function. But you are correct. Now that we're about to start doing division, that number also does represent the remainder. Okay, so let's take a look here. We're about to do this procedure. And so everybody, you see what that first problem says? Take this polynomial, x cubed plus x squared minus 11, x minus 36, and divide it by x minus 4. Now, at first glance, you just look at that and you let your brain, look at that. You might just say, I don't know. What does that even mean to divide that? Like, what does that even mean? It'd be one thing if the problem said divide 55 by 5. Then we're all on board. Okay, you just divide. But what does that even mean to take a polynomial and to divide it by x minus 4? Well, the first thing I want you to notice is that we're always going to be dividing by a factor, right? We're only ever going to be dividing by what looks like a factor. So we're dividing by the factor. What x-intercept does that represent? Positive 4. And here we're dividing by a factor. What x-intercept does that factor represent? Positive 3. Okay? So keep in mind that the factor and the x-intercept have opposite signs. So we're dividing by a factor, which could represent an x-intercept. And we're really asking about the x-intercept. Okay. So let's look at this. We have, okay. For number 30, what I'd like you to do is, first of all, we're taking that polynomial, we're dividing it by x minus 4. So dividing by x minus 4 is the same as, is the question, okay, you might want to write this down, is the question, is x, is 4 an x-intercept? It is 4 an x-intercept. Because notice it's x minus 4, so you change the sign. We're talking about the number 4, we're saying, is 4 an x-intercept? Right. So we would use synthetic division. So let's take a look. I want to divide x cubed plus x squared minus 11x minus 36. So I'm going to do synthetic division, which is 1, negative 11, negative 36. And I'm going to use the number 4. Okay, very important. We're dividing by x minus 4, but remember that's the factor, so you have to change the sign. We're actually asking, is 4 an x-intercept? Now, let's think about what that means. I have a polynomial. It's a cubic, so it looks something like this. And at most, it has 3 x-intercepts, so it has something like that. And we're asking, is 4 one of the x-intercepts? If 4 were an x-intercept, that would mean that the coordinate 4, 0 is on the graph. And if 4, 0 is on the graph, that means input 4, output 0. So what does that tell me right now? If I input 4, what should I get? I better get a 0, if all of this is true. So let's try it. Input 4, so I drop the 1, multiply, add, multiply, add, multiply, add. Worked out. I inputted a 4, I outputted a 0, and therefore 4 is an x-intercept. That's really exciting. That means that, first of all, I do know something about my original polynomial, x cubed plus x squared minus 11x minus 36. There is an x-intercept at 4. Now, what do we do with all of this information? And we already know that this is my input and this is my output. Now what I'd like to do is show us all what these numbers mean. So the rest of the bottom row actually does carry information. So here's what it means. Notice that we started as a cubic. We started as a cubic x cubed. This bottom row of numbers now gets variables, and you start at one lower than a cube, which is a square. And so you go ahead and write in, there's one here. You write in now x squared x, no x. And what we do here is we now know that my original polynomial x cubed plus x squared minus 11x minus 36 is the same as the 4 was the factor x minus 4, and now the rest is 1x squared plus 5x plus 9. That's how you read the information. That's how you read the information. 4 was an x-intercept. We checked it because the output was 0. And therefore, the x-intercept 4 can be recorded as the factor x minus 4. And then these other numbers in the bottom row actually are the coefficients for a reduced polynomial that we've now factored this part once. How does everyone feel about it? Yeah, Chelsea. Well, technically, the way you read all this information is that this number goes out on the outside. And this, a minute ago, Josh asked, is that number the remainder? And yes, that number is the remainder. It's what is the remainder upon the division. And so there's another plus 0 out there, but what's plus 0? Nothing. So we don't have to worry about it. So what we just did was we used synthetic division to factor the cubic into one factor and now this one. That's a huge deal. Because basically what we're going to do is we take our regular polynomial, which is a big long addition problem, and we start factoring it one chunk at a time. So I'm going to show you what that looks like. I start with an x to the 5th. And then I have all these terms down to a number, which I use 5, it doesn't matter. And then the first step of synthetic division chunks off one factor. And then what do I have left? An x to the 4th power, down to a number. And then the next step of synthetic division chunks off another factor, leaving me with a cubic. And then I have some other number. And then the next step of synthetic division chunks off another factor. This is what the process would look like from a bird's eye view, leaving you with a quadratic. I'll go along. And then the very last step would chunk off another factor, and I'd be done. Okay? I just made up all the numbers, but this is the process we're going to go through. Every time you use synthetic division, you chunk off another factor until you get all the way down. Okay, so visually, that's what it would look like. And visually, that's what we just did right here. I started with the polynomial x cubed plus x squared minus 11x minus 36, and I just chunked off one factor of x minus 4, leaving behind x squared plus 5x plus 9. And then, in theory now, at this point, you would continue the process. You would then take this square term and chunk that. And then at that point, you'd be done. And the whole thing would be factored. Okay, so let's all try that again now. I was just showing you how to read the bottom row of numbers. So let's try that again. Because it said to divide it by x minus 4. What we really just accomplished was factoring it. Turning it into a factor where one of the factors was x minus 4 and the rest. So let's try the next one. That's a nice one. It's 3 and the 4th. So just write down the coefficients. 3, -8, -8, 13, 6. And we want to divide it by n minus 3. So now again, walk yourself through the reasoning. If we're saying that n minus 3 is a factor, then what's the x-intercept? Positive 3. So what we're saying is that for that polynomial, I'm wondering, is 3 an x-intercept? It's like a question. Is 3 an x-intercept? Well, if 3 is an x-intercept, then the coordinate 3, 0 is on the graph, which means if I input 3, I should output 0. So that's the first thing we're going to check. Is it really an x-intercept? If I plug in 3, do I really get 0? So let's try it. Drop the first number, 3. So now multiply, add, multiply, add, multiply, add, multiply, add. Great. It was 0. So now, in fact, I do know that 3 is an x-intercept on that graph. Because if I input 3, I output 0, so that's an x-intercept. And now I can reduce now. I can change and factor my original polynomial, the 3n to the 4th minus 8n cubed. Now what we're going to do is take all this information and drop it down. I just want you to see how to write it down. The 3, which is an x-intercept, is the factor x minus 3. And then all of those terms, again, we started as n to the 4th. So you reduce that by 1 to n cubed. So now this is n cubed, n squared, n till n. And so now that is 3n cubed plus 1n squared minus 9n minus 2. And there's a plus 0 at the end. And again, that's why that's called the remainder term. But plus 0 doesn't do anything, so I'm not even going to write it down. So that's what we did. We successfully factored the original polynomial, and we broke off one factor. If you don't mind my use of language, breaking off a factor, chunking out a factor, factoring out one bit. How does everyone feel about this? I mean, this is just the definition of how to read the information off of the synthetic division. So Isaac, you see why it's so important now that you do the whole table. Okay, well, let's try another one. We'll do 32. So we've got r cubed plus 7r squared plus 3r minus 27. And we're basically asking the question, can this thing be divisible by r plus 3? Is r plus 3 a factor? That's what we're asking. So if r plus 3 is the factor, which x-intercept are we interested in? Negative 3. Right? If r plus 3 is the factor, then we're interested in the x-intercept negative 3, which means we're wondering, is negative 3, 0 a coordinate on the graph? Which means if I plug in negative 3, will I get a 0? So we take our coefficients, 1, 7, 3, negative 27, and I plug in negative 3. And at this point, we're just crossing our fingers that it outputs a 0. So drop the 1, multiply, add, multiply, add, multiply, add. It worked out. So yes, negative 3 is an x-intercept, which means, and again here, I hope that you all kind of do what I'm doing here in terms of reading this information. We now know that in here, since we started as an r cubed, we reduce to r squared, r, no r. And then what we now have is our factored expression. The -3 is really the factor r plus 3, right? Because you have to change the sign between the x-intercept and the factor. You always change the sign. And then this part is 1r squared plus 4r minus 9. And what we essentially just did is just factored it. Now I want you to notice. Oh yes, go ahead, Celine. This is just the procedure. When you're all done, since the original, watch this. When the original polynomial was 1r cubed plus 7r squared plus 3r minus 27. That was the original polynomial. When you factor, you reduce that polynomial by 1 degree. So r cubed goes down to r squared. And so that becomes the rest of the polynomial. Does that answer your question? Okay. Okay, so notice we have a lot more information out of this now. Originally, all we said was that this was the input-output. So if you just look there, all you would know is that -3 is 0 is a coordinate on the graph, which in this particular case makes it an x-intercept. And now this other bottom row of numbers turns out to be the factored form of the polynomial. It's pretty exciting that that bottom row gives us that information. Okay, maybe that's all we have to do. This was really just an introduction, so you can see how the basic process works. Let's see, I have more examples. But I think that we could be done with that. What do you all think? Yeah? Yeah. Oh, okay, perfect. I was wondering if there was an example like that. Which one doesn't equal 0? Oh, okay, great. Everybody, let's look at that. Great, great, great. Thank you, Chelsea. I was just thinking, gosh, did any of these not turn out to be 0? Because I'd like to look at one of those. So let's do 34, folks. Again, we're asking the same question. We're saying, is that polynomial k cubed divisible by k plus 1? What that means is, can this polynomial be factored into an expression where k plus 1 is one of the factors? And so, since we're asking about k plus 1, what x-intercept are we talking about? -1. So what we're really asking on number 34 is we're asking the question, is -1 an x-intercept? Because if it is, the coordinate -1, 0 is on the graph. And if that's true, then I should be able to do synthetic division with -1, and the output better be a 0. So now let's take all of our coefficients, which are 1, 8, 14, and 12. And then we do synthetic division. So you drop the 1, multiply, add, multiply, add, multiply, add. So is -1 an x-intercept? No. All of our dreams and hopes are dashed. No, it is not. So my little graph here is incorrect. In fact, where is that coordinate? -1, 5. So I know now that I do have a coordinate, but it's way up there, which is pretty unhelpful. Because really what I want is my x-intercepts and my y-intercept and my end behavior. So knowing that that coordinate exists is like finding a nickel on the street. Like, great, a nickel. What am I going to do with this? So, but what can we say? I want you all to see this. This is my remainder. This is still the reduced polynomial, and this is still the factor. You can write this as, here we go. The first one becomes x plus 1. And then since I started as a cubic, this is k squared k no k. So now I have 1k squared plus 7k plus 7. And then the 5 at the end is the remainder, and you write plus 5. So that's what we accomplished in this problem. That's how you read the information. And all I want you to know is it's true. That's true. And this is equal to the original k cubed plus 8k squared plus 14k plus 12. So if you took this original polynomial and you wanted to factor it such that such that k plus 1 is one of the factors, it's going to result in an incomplete factoring. It didn't really work. That's something times something plus something. Can I do the zero product rule on this? No, because to do the zero product rule, I have to be something times something times something, but I got a plus at the end. So this expression right here is utterly worthless, but it's true. Doesn't?
So then if we're taking a test, then we're going to have to write the factors?
Well-
Or do you just want us to have?
You have a good question. We haven't quite got there yet. You know, we're just building skills and seeing what all this stuff looks like along the way. Ultimately, our goal is to factor the whole thing. That's always ultimately the goal, is to factor the whole thing into separate factors. But as it is, I just want you to know, this is how you read the information from synthetic division. This is the full picture of how to read the information from synthetic division, which is that if you start with, this polynomial, 1k plus k3 squared plus 14k plus 12, that polynomial is equal to this. It's just that this isn't very interesting because you can't apply the zero product rule to it. It's still true. You know, if you multiplied this all out and added 5 to it, you would get the original. And so ultimately what I want to tell you is synthetic division is a powerful tool that can produce a something times something plus something. That's what synthetic division is capable of doing. It can take a plus 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 and turn it into a something times something plus something. And the only way that's interesting or helpful is if that plus something is a 0, because then you have in fact produced a factor. Okay? Yep. All right. Well, thank you very much for pointing that out. Now, everybody, let's go to your packet. This is your actual notes packet. Go to chapter 3. Now, first of all, now that you all see synthetic division, who studied synthetic division in your childhood? I don't see anybody raising their hands. I thought, Sarah, didn't you and Selena say you did it? Okay, so 2. How many? Josh? Anybody else? Brandon? Anybody else? Okay, so what you're telling me by your total and utter silence and not raising your hands is that most of you have not done this before. Is that what you're saying? Okay, because that's helpful for me to know. Okay, so we're starting here at the top of your chapter 3 notes. And what I can tell you is that all the practice that we just did, that's the practice I created for you, myself personally. And now we've basically covered a whole lot of information from this packet. And we can kind of move along quite quickly through most of the notes. So the first thing you see there is just a bunch of definitions. The program more and the packets that they have give a lot of definitions. Now, do we need all these? Let's look. It says here, the natural number n, which is the highest exponent, is called the degree. Okay, so we already knew that. The first exponent, the highest exponent, is the degree. The term an x to the n is called the leading term. And that's right, we were calling that the leading term. The real number a to the n is called the leading coefficient. So all of these little a's are the coefficients in front of the variable, and that's the leading coefficient. So keep in mind, the leading term tells you if it's a parabola or a cubic shape. And then the leading coefficient tells you if it's positive or if it's negative. So we have information in there. The real number a is 0, all the way at the end, is just called the constant term because there's no variable there. And that is the y-intercept. Okay, here they're saying if f of x is equal to that, you say that no, okay, not very important. Not very important. The graph of the function of degree 2 is an unbroken, smooth, continuous curve. Yeah, the graph of a polynomial function of degree 2 or greater is an unbroken, smooth, continuous curve, meaning you get to make a lot of swoopies and connect the dots and like that. It's a smooth, continuous curve. The domain is always negative infinity to infinity, meaning your polynomial will continue going to the left forever and it will continue going to the right forever. So the domain is always all real numbers. The graph will change directions at most n-1 times. Now that's interesting, a turning point. How many times does my graph turn? So I'm going up, turn, that's one turn. And then turn, that's a second turn. And then turn, that's a third turn. And then turn, that's a fourth turn. And how many turns did I have? And yet my polynomial was 50. So that's just more interesting information. If it's x to the power 5, you have at most 5 x-intercepts. And if it's x to the power 5, you have at most 5 minus 1, 4 turning points, meaning it could turn on itself 4 times. Okay, graphs will cross the x-axis at most n times. That's what we've learned. So the degree is how many times you could have an x-intercept. It could be less. And the leading term will control the end behavior. Okay, so that's what all those notes said, right? We basically talked about all of that. And they just have it written down for you there in a nice, concise way. All right. The next couple pages, go ahead and turn the page, talk about material we've already discussed. So it's talking about end behavior. So you can see here, this is exactly what we said, end behavior for an even function. That is x to the power of an even number. It'll always essentially be parabolic. But you'll notice that as that even exponent increases, it gets a little flatter along the bottom. But it still looks like a parabola. So that's what we call even end behavior. And now this is called odd end behavior, which we're going to talk about. So again, you can just look back at this page. You can go home tonight, pour yourself a nice tall glass of iced tea, sit down, reread through all this, and say, yep, okay, that's what we talked about. Okay, the next couple problems, just examples, we can talk about them. It says find the degree, the leading term, the leading coefficient, the constant term, and the end behavior. All right? So first of all, what's the degree? The highest power on x, right? So here the degree is 5, which means you can have at most 5x intercepts. Here the degree is 2, which means you can have at most 2x intercepts. What's the degree here? 4, because the degree is also the number of factors. Because when I multiply all those together with FOIL, first, second, or last, I'm going to end up with x to the 4th, something, 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 plus 24. Because I just multiplied 4 times 2. So this degree is also 4. The leading term is the term with the highest power. The leading coefficient is the actual number on the leading term. And then the constant term is always the term at the end, which is the y-intercept. And the end behavior you get by whether or not it's an even or an odd function. Yeah. You're kidding. That's not what you had? Really? Yes, it is. Oh, I see that. Oh, no, quite a few of these are different. Wait. How strange. What on earth? How did this even happen?
Yeah, I mean, have it.
What?
Oh, there I am.
Okay, so everybody, we're on page 3, right? Yeah, and I completely agree with you. These are different. That's strange. Not sure why these are different. In any case, that whole page, if you like, you can just cross it out and I won't grade you on it. How about that? Because we've already basically talked about this. We've talked about what these terms mean, and that's fine by me. You can just cross out the whole page. Okay, but geez, I hope that we match up later on. If my page doesn't match yours, I need to just update my slide so it does. Okay, hold on a second. Oh my gosh, I'm clearly in a lot of trouble, folks. How did this happen? Oh. Okay, folks, I need a moment. Clearly. So you can talk amongst yourselves. Oops, I just unplugged that. You can meditate. You can tell each other jokes. And I will be right back with you. How, oh how did this happen? Oh, right, because all of your packets started on 3.0, right? Okay, and then we just basically skipped through all that. Oh my, yeah, there's a lot. Oh, and then we finally get to that. And then it's different. I cannot believe it. All right. All right. Well, first of all, folks, the first thing you can all do is you can tear off the whole section that's 3.0 because that's not for you folks. So that'll make it easy. So I don't know how many pages that is, but you can take off the
Polynomial arithmetic?
Yep, all that, all of 3.0. We're going to start together where it says 3.1 graphs of polynomials. That's where we begin. Very sorry for the confusion, folks. You can all use those extra pages to make paper airplanes. Probably been a while since you made a paper airplane. Oh, I'm sure that they do. Okay. I think I've gotten enough. All right. I just have to email this to myself and I can put it up on the screen. Folks, just so you know how geeky I am, this is normally the stuff of nightmares for me. Like I'll have a nightmare that I show up to class and my PowerPoint isn't the right PowerPoint. And then I'm like sweating and shaking trying to fix it all. So I'm living through a nightmare right now, just so you all know. I think I'm handling it pretty well. All right. You're like, Mr. G, if that's your nightmare, that's not bad. I'm on no chased by a monster. Okay. Now I know a second ago I just told you all to scratch that one page out. We might look at one or two of those examples just to make sure that we all have an example for when you go home to do your homework. So, oh, that's not good. So we are here. All right. Thank you so much. Now, is that what you all have?
Yes.
Goody gumdrops. So, I think what I'm going to do is put this on the board. It'll be a whole lot easier if I can just write on it instead of that, maybe. Yeah, if you put an X through it, that's fine. I'm sure you can still see it. Yeah, right. There we go. You took a Sharpie and scribbled the whole thing out. Okay, is it turning on? I think it's turning on. I think it's turning on. All right, back in business. So let's just do a couple of examples, and I'll do the very first one. Let's diagram it. So the degree is the 5. That is your degree. It's the highest exponent. It's also the maximum number of x-intercepts. The leading term is the entire 3x to the 5th. Leading term. The leading coefficient is just the 3. Yep, coefficient. And 1 is the constant term, which, as we know, is the y-intercept. And the end behavior is given by the degree. So the degree slash end behavior. Right? So that's where we look for information about the polynomial. It's pretty wild, isn't it? That just by looking at a polynomial, there's so much information sitting there telling you information about what the graph will look like. So how about one of these other ones down here? This one is helpful because we've already seen an example like it. you would have to fake FOIL that. And by fake FOIL, I mean just start the FOIL process. You don't actually have to do the whole thing. So negative times negative times negative times negative is positive. 4 times 3 is 12 times 2 is 24. So that's all we really have on this one. So now we could still get all the same information, right? So our leading term is 1x to the 4th. The leading coefficient is just a 1. The degree / end behavior is the 4. And the y-intercept is the 24. Now, just for a challenge, because I know you all want a challenge. Say, Mr. G, let's have a challenge. What about this thing? How would we even begin to read this thing? That doesn't look anything like what we've been doing. However, we could write this out in a more explicit way. So for instance, notice I have a -2, and then x cubed is really x times x times x. Right? X cubed is x times x times x. And what's in there with it? X plus 0, x plus 0, x plus 0. And then we have the x plus 1 term. And then we have x plus 2 squared, which means you're multiplying x plus 2 times itself twice. So x plus 2, x plus 2. So, see what I did there? I wrote it out in like long form to see what on earth was actually being multiplied there. I had a -2, x times itself 3 times, which is really x plus 0 times itself 3 times, the x plus 1, and then x plus 2 multiplied by itself twice. So what do we get out of all of this? Well, we know that we have an x-intercept at 0. Let's look. We have an x-intercept at 0. I know it's listed multiple times, but that's okay. You can list it multiple times. There's still just an x-intercept at 0. There's an x-intercept at -1, and there's an x-intercept at -2. Now, furthermore, if you did your fast foiling or cheap foiling, the first term is going to be x times x times x times x times x times x, which is x to the 6th. And then the last term is going to be 0 times 0 times 0 times 1 times 2 times 2, which is 0. That's just cheap foiling all the factors. But then I'm multiplying all that times -2. So my cheap foiling would give us -2 x to the 6th plus plus 0. So if you really did FOIL that whole thing out, you know that you'd have some polynomial that starts with -2 x to the 6th and ends with 0. And we don't know what all those middle terms are because that would take a lot of time to actually multiply all that out. But now looking at this, we can now say our degree is 6, which means our end behavior looks like a parabola. We know that the first term is negative, which means is our parabola facing up or down? Since it's a parabola and it's negative, it's facing up or down?
Yeah.
It's facing down. So now we know a lot about the end behavior. We're actually looking at something that looks like this. So this leading coefficient gives us part of our end behavior information, the fact that it's down. The 6th degree tells us the end behavior and that it's parabolic. And we know the y-intercept is 0. And again, this is our leading term, our leading coefficient, and the degree of end behavior. Again, that's a lot of information that you can extract out of a polynomial that we didn't even multiply all the way out. Could I draw a pretty good graph of that? Yeah, I think so. I would have an x-intercept at 0, at -1, and at -2. And I have a y-intercept at 0 as well. And it's an upside down parabola. So far, I have something that looks like that. I'd have to do a little more analysis because at some point we're going to talk about slices and bounces. So this graph would actually end up looking like bounce, slice, slice. We don't know how to do that yet, but I'm just saying that this is where we're building. We're building up to the ability to make a nice sketch by hand. Okay, I know my phone just went off. So let's see what we can do in the time allowed to us. So we have some more notes. This is what you have on the next page, right?
Yes.
I'm all nervous now that you're tagging this to what I have on the board. But no, what I have now is what you have. Now, I tell you what. There's a lot of information up on the board. And honestly, I feel that most of these definitions are written in such a way that it'd be better if we just talk about what these concepts are first and then go back and read it. So let's just leave that alone for a minute and go to the next screen and try some examples. So it says, find the real zeros of a given polynomial and their corresponding multiplicities, and use this information along with a sign chart to sketch the graph of the polynomial. So what do I really want us to do here? We're going to learn about bounce and slice. All right? What's that? Oh. All right. So it says, find the x-intercepts. We can already do that. And then use this information along with a sign chart. Well, I don't know if we'll do the sign chart. And then sketch the graph. So everyone take a look here. I want you to go ahead and write this out as factors so that x is actually x plus 0. And the x plus 2 is really x plus 2 times x plus 2. So start there. What's the, if I did do a fast FOIL of this, it would give me what? X to the third, and then the last number would be 0. Because 0 times 2 times 2 is 0. So far we know a lot. We know that we have a cubic graph, which will end up looking like that. Right, so the x cubed means my graph will look like this. I know my y-intercept is 0, so I can go ahead and put a dot at the 0. And I know that I have an x-intercept where? -2. So I'm going to go over here to -2. Okay, that's what we know so far. We also know that because of the end behavior, I'll have a tail coming out this way and a tail coming down that way. Okay, so this is called curve sketching. We're using all the information that we know how to extract from that information, and we're starting to sketch a curve. The thing we're learning right now is about a bounce and a slice. So now that we already wrote it out like this, I want us to rewrite it as the factors with exponents. So this is actually, got to come down here, x plus 0 to the power of 1 and x plus 2 to the power of 2. Now, I'm going to create an analogy here for you. You know that when you have an even power, it looks like a parabola, right? Whereas when you have an odd power, it looks like a cubic. Right? So that's end behavior. We already know that. What I want you to notice is that if the exponent is even, what does the graph do? It bounces. Like if you dropped a ball on the ground, it'd go down, bounce, and go back up. So an even power always means bounce, even with end behavior. Because that's what a parabola does. It's coming down, but then it comes back up again. So an even power means a bounce, whereas with an odd power, a cubic function does not bounce off the x-intercept and go back down again. The odd-powered functions come up, across the d-axis, and keep going up. And so we'll refer to any odd power as a slice. This is a general rule which will hold true for the individual factors that we're looking at. So for sure, even-powered polynomials look like parabolas, and odd-powered polynomials look like cubics. But also, even powers imply a bounce, and odd powers imply a slice, meaning it goes through the x-axis, going from the negative side to the positive side, or going from the positive side to the negative side. So let's look at how we can interpret this now. This is a factor referring to the x-intercept of 0. And this is a factor referring to the x-intercept of -2. And what I know about my x-intercept at 0 is that because the power is odd, it's going to slice through. Whereas here, my x-intercept of -2, because the power is even, the graph is going to bounce at that x-intercept. So what do we do here? On my graph, I'm going to start on the left. I was working left to right. I'm approaching the x-intercept of -2. Should I slice through it or bounce?
No,
I'm going to bounce. So I'm going to go up, I'm going to hit it, and I'm going to go, boing. I come right back down. That's what I'm calling a bounce. Whereas now I'm approaching my next x-intercept, and that one is at 0. That's a slice, so you just slice right through. So that was bounce, and this was a slice. And the good news is, we're going to end class right now, and you now know everything there is to know about curve sketching. So there's no more information. We've covered all the information about curve sketching. You can now take a polynomial, whether in polynomial form or in factored form, and you could now sketch it out accurately, right? There's still a lot to talk about, but that's what we get to today. So what does that mean? Today's Wednesday. We did not finish 3.1, so what homework is due on Monday? Nothing. Do we have class on Monday? No. So I'll see you all Wednesday. We will proceed from where we are, and I'll give you your test back. Thank you very much, folks.